Masazumi, senior research scientist here. First, I'm a physicist. And then I'd like to introduce the concept of renormalization, which is originated from high energy physics. And Japanese translation of renormalization is pretty common. And the subtitle is word by Socrates, and in Japanese it's Nuchi no Chi. And I'm thinking that this word is a kind of good slogan to explain renormalization. Okay, so let me start with a brief summary of what's written in textbook. And purpose of this talk is to introduce a concept by using simple example. So even if you don't understand this, so don't worry. Okay, let me start with some historical thing developed by Tomonaga-san, Schwinger, Feynman, Dyson, and so on. And yesterday I learned that Tomonaga-san joined the LIC in 1932. They were working on quantum electrodynamics, which is a special case of field theory. And field theory is basically quantum theory of field. And we typically take space-time to be continuous. And field and in continuous space-time, so we have infinite many points. And it is well known that by using very naive definition of quantum field theory, and if we try to compute the physical quantity, we get basically divergence everywhere, especially because that we have a very high energy mode essentially coming from continuous space. And then they developed a prediction called renormalization, and slogan is here. So we get a naive divergence, but if we add another source of divergence, or if we subtract the divergence infinity in some way, then finally by infinity minus infinity, we get final result. And when I learned this first time, so I was not sure what does this mean. And then we replace the value of finite value by experimental value. And so if this happens for all the physical quantities, so I think that theory does not make sense. Theory does not have a predictability. But it is not that at least for QED or some other realistic field theory, this happens only for finite number of physical quantities. So by using finite input from an experiment, so we can predict the infinite number of physical quantities. So in this sense, this theory, this prediction has some predictability. And indeed, maybe most precise theoretical accurate theoretical result was obtained by using this prescription reading. And there is a modern explanation of this kind of thing or related things developed by Wilson. It's related to the concept called renormalization group and effective field theory. And he pointed out that properly defined quantum field theory do not have infinity. And previously, we have a naive definition of quantum field theory had an implicit assumption that theories are correct to arbitrarily small distance. In general, we don't know what will happen to very, very small distance, but unless we have experimental result. So in general, we only know low energy effective theory. And also, there is a class of effective field theory insensitive to details of actual very high energy behavior or very small distance behavior. this class of theory is called renormalization theory. And now I'd like to explain this concept not by using quantum field theory. And I will use I will work on a particular example of quantum mechanics. And for most of cases of quantum mechanics, we don't know, we don't need renormalization, but it is known that there is some special cases actually need renormalization. Okay, so let's consider some one-particle non-relativistic quantum mechanics with potential like this. Yeah, A is some positive constant, and pictorially potential like this. So we have our origin in divergence, and in the negative region, we have an infinitely high voltage. And there is a equation called time-independent Schrödinger equation, which determines the value of energy, which is supposed to determine value of energy. And this is technically just let me take unit p equal h by 1, and also let me also take mass of particle to be 1. Yeah, because I'd like to interest only conceptual thing. Okay. So technically, we'd like to consider this problem. Let's consider this ordinary differential equation. And here is some constant. It's physically energy. So this is an eigenvalue problem of the ordinary differential equation. And now I'd like to ask the following question. So is there solution? Is there any normalizable solution in this setup? And more precisely, square integrable solution. So now this is a technical question. And so I skip some details, but it is not that necessary condition to have a normalizable solution. This. So first, it should be 0 in infinite world regime, and also it should go to 0 in infinitely far away. Also, energy should be negative. Okay, let's look for the solution of this differential equation. It is known that there is a solution for when this coefficient is larger than some value, which is 1 over base. And solution, it is known that we have a solution described by modified Bessel function. here is just constant. And this is a modified basic function. And here I define some parameters like this. And here is modified basic function. And this is solution and positive regime. And this solution, so we have this solution for any negative E, real E. So either continuous also can be minus infinity. And it can be, the fact that it can be minus infinity sounds odd because this implies that the theory itself is unstable. So in this sense, so this setup apparently looks like fit. Okay, now I'd like to explain physicist way of thinking this setup. So instead of naive quantum mechanics, I'd like to let us consider regularized quantum mechanics. So instead of considering this potential, let us consider potential given by this. So now here becomes a value epsilon. It's not zero. Then later I'd like to come back to epsilon to 0. And now instead of considering this boundary condition, let's consider maybe here boundary condition given by this. So this is saying that psi epsilon. So this is saying that the psi should be 0 at the infinite large wall. And form of the solution itself is the same, even for this potential. But because of this boundary condition, we have an extra condition saying that this function is 0 at some point. And this changes spectrum dramatically. So this is a special function, but if we consider the very small regime of kappa epsilon, this condition is boiled down to this condition. This can be satisfied if this argument is integer times pi. So therefore, we have this condition. And here n is an integer. And the value of kappa related to energy cannot be now continuous. So there is a label integer to label energy. So now energy becomes discretely distributed. and also there is the minimum energy, which is given by energy with n equal 1, and value of energy is given by this. And this is not the end of the story. So I'd like to come back to epsilon to 0. First of all, if we take naive epsilon to 0 limit, we just get the infinity again. Yeah. So, but yeah. So now let us apply renormalization groups. Yeah, instead of taking naive epsilon to 0 limit. So we also change the parameter t depending on epsilon, such that epsilon to the limit of the ground state energy is finite. Specifically, this is possible by taking the epsilon like this. Gamma is an Euler constant, and in epsilon to 0 limit, this goes to 0. And then this combination can be finite for n equal 1. And under this condition, or under this limit, we can compute other physical quantities by using E1 and G, and we can remove the kind of artificial parameter epsilon. E1. So we can predict other physical quantity by using G and E1 without using epsilon. And so this is the end of explanation of physicist way. And I was preparing a more mathematical way using the self-adjoint extensions. But since I'm running time, so let me explain this very, very briefly, maybe in 1 or 2 minutes. But it's not only differential equation, but in quantum mechanics, it is known that state after belong to is belonging to vector space called Hilbert space, and the operator is a map from Hilbert space to Hilbert space. And importantly, value of physical measured value of physical quantity is described by eigenvalue of operator called self-adjoint operator. Definition of physicists often confused between self-adjoint and Hermite operator. And this is a Hamiltonian operator. Basically, Hamiltonian operator with having the same domain for same domain with conjugation of operator. And for energy, when if we take physical quantity to be energy, corresponding operator is called Hamiltonian. And Hamiltonian operator for one-particle quantum mechanics is famously given by this differential operator. And it is known that most cases, like most cases of potential, this Hamiltonian is self-adjoint. Usually it's self-adjoint. This is reasonable since we think that energy is physical quantity. But for this particular case, it is known that whether it is a self-adjoint depends on boundary condition. It depends. So self-adjointness depends on boundary condition. Boundary condition around x equals 0. And relation to the renormalization is that if we try to make Hamiltonian self-adjoint in this setup, it is known that there is a one parameter family parameterizing boundary condition, and that parameter is related to the epsilon. But a priori, we don't know which parameter of boundary condition is appropriate without comparing with experimental value. So this is a kind of mathematical understanding of renormalization for this setup. And I'm not sure if there is a similar argument for quantum field theory. So if you know something, please tell me. Okay, that's the end of my talk. Thank you very much.
Thank you very much, Honda-san, for very interesting talk. So, questions?
Yes.
You know why your commutator algebra P and X are independent of the potential? Because you know, in the quantum mechanics,
yes.
we assume P and X commutator independent of potential. Yeah. And that's somewhat related to your argument. Namely, the point is that the commutator algebra or quantization is valid and infinite energy essentially. Therefore, potential is not important. So, whatever potential you have, commutator algebra is same, P and X. And that in that sense is very strange. Because you know, if your potential is very strong, people might say commuted algebra is modified, but that's not. Commuted algebra is always fixed. Therefore, your theoretical equation is also fixed. And that is, in a sense, assuming that your equation is valid for the infinite energy.
Okay, if your intention question correctly, so we have a usually this kind of computation relation, but if we take kind of naive trace, and for it this is like a finite size matrix, so we get the contradiction, but this is not a valid equation because when Hilbert space is infinite dimensional, so we are not sure. So since we have an infinite sum, so it is not guaranteed that we can change the infinite summation, and maybe what you said is related to when we consider kind of trace by using energy eigenstate. Yes.
You are going to some more complicated problem. But my case is a very simple one.
Yes.
Namely, why that first quantization condition is independent of potential. And that means, we are quantizing the theory. Assuming that, theory is, valid at the infinite of energy. Therefore, potential is not important. And in fact, when you define the commutator as in the operator sense, that's a short time limit. Time limit case, we define the commutator. And therefore, in a sense, uncertainty principle implies that we are looking at the infinite energies, in a sense. But somehow, physics is to finite energies. And so, sounds strange, but anyway. But
it's
I
very
have to
deep
point
question.
out that question, okay? Therefore, and in fact, many young people do not know why, quantization condition is independent of the potential. And that's a physical reason that's okay. That is defined as the infinite energy.
It should strongly depends on starting point of the discussion. I think so.
Technical.
Yes.
So this analysis shows that A equal 1, 8 is a very special point of the potential.
Yes.
Where this limit, where this scaling limit is near the boundary of the coefficient.
Exactly. Yes.
So from the symmetry perspective, where is there any A equal 1, 8 is a special point?
I'm not sure about symmetry, but from this viewpoint, that A equal 1, 8 is very special.
I guess that there must be some kind of conformal symmetry or the scale symmetry. So it's kind of fixed point first. Maybe if we consider kind of analog of beta function from analog of this running coupling. This is one point. Also, cases when cases when boundary condition gives the self-adjoint Hamiltonian operator is also the value is also crucial on examining when it is self-adjoint. Yeah. So I think this phenomena is very specific to this 1 over x square potential.
Yes.
I wonder why it is not 1 over x instead, but 1 over x. Because 1 over x seems to have scaling variance.
No, this case is scaling variance. Yeah. For one dimension case. And for the two-dimensional case, delta function is scaling variance. Or 1 over x is scaling variance. Yes.
So, but then, but it doesn't explain why a equal 1/2. That coefficient is a very, very special. What's the reason?
I'm not sure. Just looking at the Schrödinger equation for NEA, it apparently has a scale invariance. But we have an anomaly of scale symmetry in this setup. And actually, I don't know. I don't have an intuitive argument on why special point is. There is a special point.
So if A is smaller than 1/8, then the spectrum becomes discrete. Without before taking introduced without introducing this cutoff.
Yeah, without introducing a cutoff epsilon, we don't have a.
If A is smaller than 1/8, then what's the spectrum?
Yeah, we don't have.
It's a discrete?
No, I think for without epsilon there is no negative solution, normalizable solution to give a negative energy.
State. Only continuum?
Yeah.
1s should be the exact point that the bound state can have.
Oh, I see. Okay.
Easy question.
Yes.
In the beginning, you mentioned the renormalization and also effective theory at low energy.
Yes.
What is the useful effective theory in this case?
Okay. So since we don't have another direction in space, so it's not easy to naively apply. But I would say there should be in general there should be similar ways to regularize this setup, and I think the epsilon to 0 limit depends on details of how to regularize this setup. So detailed counter should be counterpart in normalizability. Yeah. Yes.
So
yeah.
In general, this type of prescription is not unique, right? There are a few different ways.
Yes.
How do you say which one is good and which one is not?
Well, for the limit, there is maybe one criterion would be to look at symmetry or whether regularization preserves symmetry. But anyway, for the limit, we should get the same result for renormalizable case. So whether it is good depends on maybe what you want, what you want the scheme to satisfy. I'm not sure. Yes.
So here we renormalize a bit. So I don't understand why this is why this is renormalizable. It's only finitely many parameters.
Okay. Actually, sorry. I'm not sure about renormalizability in this particular setup because I showed.
But from the math theory, maybe you can find how many parameters.
Yeah. From this point, there is only one extra parameter. Yeah, it can be proven by calculating so-called deficiency index or something. So there is only one.
So that should be somehow similar to usual dimension count.
Yeah, if we regard this as one dimension quantum field theory, there may be argument. I'm not sure.
I'm not sure.
Yeah. Yes.
So you get some kind of learning public model. Do you have the renormalization equation or data function?
Yeah. Maybe if we
that function of G or
I think if we regard this as an energy scale,
renormalization,
we can get something like a renormalization equation. Yeah. And it's apparently it's like asymptotic free theory.
And beta function, the function of public model, or usually quantum field theory, beta function is the function of G. Is that safe?
I guess so. Yeah. We can consider derivative of this by using E1. Well, maybe. I can calculate.
Okay, so if there's no further questions, let's thank Honda-san again for his very intriguing.
I have one question to mathematicians. There are some mathematicians here. So I think this kind of theory is one of the important subjects in mathematics, especially spectral theory or so. In mathematicians will have any comment what kind of subject or what mathematicians are interested in this kind? If some of you have any comment,
I don't know what. So I think one of the questions you proposed in the last episode is that is there any kind of theory? So other setting, but currently all such one I know is the one given by the work of Costello. It was, to my understanding, some is the attempt to make it mathematically rigorous, some renormalization framework, but currently, I think this is not very complete. Only covers some very specific cases, like some observation theory or like that. So
so this is one example. So I wonder how general it is, or whether it can be generalized to higher dimension.
Yes, I don't know. Sorry.
Okay, thanks.
Then I just mentioned that some people are critical about the Ken Wilson's idea of renormalization. So maybe it is interesting, and I don't know precisely why, but anyhow, that's not the almighty or all the people accepted Ken Wilson's idea. There will be some cut off and so on.
That guy's made like this way, right?
All right. So then let's thank Honda-san again for very interesting talk. Thank you very much.
Thank you.
All right. If there's no further announcement, I just stop facilitating and let people